So I'm Bart Paulhamus. Good afternoon. I'm from Johns Hopkins University's Applied Physics Laboratory, and this work is a collaboration that we're doing with the Intuitive Computing Laboratory up at Whiting School of Engineering. As real quick background, the Applied Physics Laboratory is a division of Johns Hopkins University. We're about 7,000 people. We're located in Laurel, Maryland. Within the Applied Physics Laboratory, I work in what we call the Intelligent Systems Center, and that's a collection of about 100 research scientists and engineers from artificial intelligence, robotics, and neuroscience. And APL as a whole is primarily focused on the Department of Defense, but within that we categorize our work into what we call mission areas. One of our newest, the newest mission area that we have is national health. And the goal of that mission area is to revolutionize health through the use of science and technology. And where that overlaps with the Intelligent Systems Center, or one area at least, is in the area of assistive robotics. And that's what I'll be talking about. My research interest in particular is focuses on brain-computer interfaces to control robotic prosthetics. And in particular, when you have that disconnect between a high degree of freedom robotic system and a very limited dimensionality in the control signal that you're able to get from a brain-machine interface. And this idea that I'm going to share today is one of our newest concepts in there, so I'll be interested in any feedback along those lines. So to jump into it a little bit, the goal here of this research is to develop a novel control approach for shared autonomy. And basically we're striving to get some of the advantages of teleoperation with the advantages of a more autonomous system. And I'll be walking into that a little bit more. But if you think about it in two dimensions, the amount of burden it puts on a user and the amount of adaptability that the user has in an environment, those are two dimensionalities that we'll be talking about. So to start with, a classic teleoperation, here we have the modular prosthetic limb that has 24 degrees of freedom. And on your left, the limb is being controlled by a direct neural interface. So this patient, Jan, has a brain-computer interface that's a hole in the skull, and it's directly into the brain, and she can send signals to control all of those degrees of freedom. Likewise, on the right, one of our scientists is controlling it using a cyber glove. So basically, it maps every single degree of freedom on the real hand into that robotic hand. So with the teleoperation, basically the control paradigm is mapped one-to-one. Kind of on the other extreme is full autonomy, or a shared autonomy, at least from a supervised autonomy perspective. So here on your left again, we see a brain-computer interface. This is a different patient, Eric. His control is a little different than Jan's. He's sending higher level commands to the robotic arm. So he's sending a command, bring me a drink. And the robotic arm and a perception system then is executing that command. On the right, it's more of a conceptual video, but it kind of shows the same kind of paradigm in an augmented reality paradigm. And one of the big differences here is it's less user burden for these users to do this, but they're limited on the amount of tasks that they can do. So on the right, you actually can see there was only like 5 icons that popped up. That's all the user can use the arm for. In Eric's case, you can kind of see us cheating with some tape there on the table and things like that. So he can pick up a bottle, but he can't pick up much else without retraining the system, and the bottle needs to be in a particular location. So that kind of showcases the limited robustness to the environment. So this is kind of a taxonomy that we were using to try and explain this new level of control. So I just talked about teleoperation and fully autonomous. And when you think about various versions of shared autonomy, you have anywhere from supervised control, which I also showed, to a more of a partition control, where you would take, in this case, there's 7 degrees of freedom needed to control the robotic arm, so you very much partition those in two. the human controls a few of them and the robot controls another. If it was a robot arm, maybe the human's doing the Z coordinate and the robot's doing X and Y. With the blended control, we saw some of this from the Toyota talk. The human and the robot are both providing control inputs, and some kind of arbitration function or blending function is combining those two ultimately into that control there. What we're talking about is something a little different here, where the human will provide a small number of inputs. The machine intelligence will amplify those to provide all of the inputs needed to control the arm. And the feedback loop comes back to the human. So in some sense, it's more like a teleoperation format that the human is always in control of this. But it also looks a little bit like supervised control in that the human is providing limited inputs, and then the machine artificial intelligence is amplifying that. So how does this work? This is the approach for amplified control. So we use a deep neural network, and basically we learn a policy from the state to create actions. You can do this any way you want. You can use reinforcement learning, you can use supervised learning, behavior imitation. But the key thing is that you insert a bottleneck into your deep network. Okay, so once the policy is completely learned, then we chop the network in half at that bottleneck, and the human will then provide the inputs at that bottleneck. So in this case, the robotic system required 4 inputs to control it. After we chopped it in half, the human only needs to provide 2 variables to control this robotic platform. However, these are latent variables, and they have no interpretability. So the human really has no meaning behind what those are. They're basically just numbers from -1 to 1. And the human needs to kind of, through trial and error, figure that out. And our hypothesis is that the plasticity of the brain, especially if this was a neural interface, would be able to quickly adapt and learn what these latent variables do and how they work in order to control that prosthetic arm in that way. So as far as some preliminary results, we kind of focused on trying to validate some of these underlying intuitions. So the first one was, can we actually build some bottlenecked deep neural networks that would not sacrifice performance and still be able to carry out some robotic tasks? And then the other one was, could humans actually use these uninterpretable latent variables to control a machine properly? So getting after the first one, we created a simulation environment with a robotic arm, and the task is to basically grasp that little cube and lift it up. And we created 100 trajectories of end to end. We divided up into 3 of these primitives, so we had 300 trajectories total. And each trajectory was about 150 to 300 time steps. We used that in a supervisory learning fashion to train up a neural network. On the input side is the state space. It has 18 nodes. And on the output side, we have 7 nodes for the action space, basically controlling the end effector and the open and close of the gripper. And the question that we asked, or the parameter that we played with, is what would be the effect on performance by bottlenecking this latent variables, and how much could we bottleneck that? So here are some of the results. The y-axis is the mean squared error of the joint angles as a function of the number of latent variables that we had. And we show all 3 primitives there. And you can see that for some primitives, the error, it's very robust to the number of latent variables. And for some primitives, it starts to degrade very rapidly, especially when the latent variables get too small. As you could probably guess, this has a lot to do with the variability of that primitive trajectory. So the orange up there, which is the grasp, if you think about the 7 nodes that are in the action space, it's really only one node that's doing much, the open and close. The other nodes are pretty stable. So it's very tolerable to squishing down the number of latent variables, as opposed to the green one, which has a lot more standard deviation there. You need more latent variables to capture that. But given that it has 7 output nodes, we were pretty successful in getting it down to 4, regardless of the primitive there. So the second question then was, could a human actually use these uninterpretable latent variables to do anything meaningful? For that, we have a different context. So this was a little 2D simulation environment. The video's on it. Yeah, okay. A little 2D simulation environment. So there's a robotic arm shown in blue. The one on your left doesn't move, but you can kind of see it moving in the screen on the right. This robotic arm is basically a wheel and straight segment joints. So there's 5 of them there. And the goal is to get the end effector onto the red dot, or I think within the circle even. We used a deep reinforcement learning algorithm to train up a policy to do this. And the bottleneck network collapsed it down into 3 latent variables. So the output is 5 variables controlling each of the joint angles of the 5 wheels. And then what you can see on your right is one of my colleagues using a PlayStation joystick can control the 3 latent variables. But again, there's no interpretability. It was just, can you actually get the end effector to the circle? And we kind of did a bunch of randomization, and the engineering team played with it. And basically 2 things popped out. I mean, one, we were able to do it, so you could actually do it. The other one was the more we did it, the better you got at it. So you did kind of learn it. We didn't really quantitatively study that or anything, but it gave us hope that there might be some merit here. The other interesting side note is some of us were better at it than others. We're not really sure what to take from that yet. So kind of in summary, this is kind of a novel approach. We're calling it Amplified Control for obvious reasons. The preliminary results are kind of encouraging. The next steps, we're going to do a human subjects testing and be a little more rigorous in this with a physical robotic arm in a assistive robotic paradigm. The limitations right now, some of the future work, we're really interested in, with the brain-computer interface, that data is very noisy, so we'll actually be able to work with noisy input data. The human learning assumption, how long does it actually take to learn this, will be interesting. And a lot of algorithm extensions, anywhere from the generalizability to how many primitives can we tolerate, and some of the shaping on the latent variables as well. The applications, I've already referenced a few in the human and brain-machine interfaces. Also, unmanned systems for national security. Right now, some of the DoD autonomous robots, one robot might require a team of 5 people to control it because there's so many degrees of freedom and we only can control so many physically. So if something like this could decrease the number of team members needed to control these robotic platforms, we'd be interested in that. And also moving into the non-physical domain. So things like cybersecurity is something that's very big to us at the Applied Physics Laboratory. So could this help us control cybersecurity kind of platforms as well? With that, I'll end the talk and open up for questions.
Yeah. Out of curiosity, in terms of the success users had in controlling these devices, was there any correlation to their experience with previous experiments with these devices? I know with EMG control, often there's a correlation between practicing the skill of actually sending the same signal over and over again, getting consistent results.
Yeah, we didn't, I mean, this was not very thorough. It was kind of like the 5 people kind of on the engineering team that went into it. So when we do the human subject test a little more rigorously, we're going to try and tease that out. But from what we could tell, all of us had familiarity with a PlayStation joystick before, and we didn't see anything really pop out in that dimension. But good question.
With designing this human subject research study, are you guys going to be recruiting for different age ranges or ethnicities, or are you is the first step just going to be trying to get as many people as possible into the study? Have you thought about how you're going to design that study?
Started thinking about it a little bit. We're probably focused on getting the robotic system working right now at the moment, but you know, probably the first study will be recruiting at the Applied Physics Laboratory and up at Hopkins, so the demographics will probably be in that range. We do have some partnerships where we have access or teaming with actual individuals with disabilities, so if we can try and get some of them involved, that would be good too. So, and that's what we're hoping to do. I saw back here.
I'm just wondering, so how would someone with a BMI go about controlling those latent variables? Because, I mean, obviously with a joystick you have, like, you can explicitly control the inputs, but like motor control, the brain already kind of like knows how to do that, but how would someone with a BMI actually control the latent variables?
Yeah, so Jan, who was one of the first patients, she I think in this video fed herself a chocolate bar there with that robotic arm. A video I didn't bring, one of the things that we did was hook her up to a Microsoft flight simulator so she could fly an airplane. And the way she learned that was roll her wrist left and roll her wrist right was banking the airplane that way. And in the beginning, that's what she was thinking about. But after about an hour, she said, I'm not even thinking about my wrist anymore. I just think fly left, fly right. So we think that same kind of concept will apply here.
Great, then let's thank our speaker again.
Cool. Thank you.